Okay, Borger High School Chemistry. We're ready to start on Unit 10, Gases in the Kinetic Molecular Theory. This is Ms. Howard. The state of Texas says that you guys are going to be responsible for describing and calculating the relation between pressure,
mole temperature for an ideal gas as described by Avogadro's law, Boyle's law, Charles' law. I spelled Charles' law wrong. We'll ignore that. Dalton's law, ideal gas law, and the combined gas law, although they didn't come out and say that. If you put Boyle's law, Charles' law, and, oh, Gay-Lussac's law's not on there. Yes, there's a Gay-Lussac guy on there. You get all those together and you get the combined gas law. You also have to perform stoichiometric calculations, including determination of mass and volume relationships between reactants and products for reactions involving gases. C9C, you're going to describe the postulates of the kinetic molecular theory. And C11A, you're going to understand energy and its forms, including kinetic energy, potential energy, chemical energy, and thermal energy. I have a video for you. Let us hope it works. Maybe it'll work. Maybe.
Are you ready? You wanted them. Now you've got them. It's atomic energy with molecules in motion.
Molecules are atoms that are bonded together. They're hard to see and they're difficult to measure. But if we look real close, we can see them moving. They vibrate, they rotate. It's like they're proving that nothing's at rest, that everything swirls like an ocean. It's kinetic energy, molecules in motion. Molecules in motion.
Molecules are moving all the time.
Molecules in motion.
Molecules, they keep us energized.
If molecules absorb energy from their surroundings, they move faster and faster. That's quite astounding. Just like the kinetic energy rises with molecular motion, the temperature also increases with all this commotion. Kelvin is a unit of temperature, like Celsius and Fahrenheit. And temperature is a measure, and be sure to get this right. It's a measure of molecular movement. So let's review and delve in. Energy rises with molecular movement, as does the Kelvin. Molecules in motion.
Molecules are moving all the time.
Molecules in motion.
Molecules, they keep us energized.
In liquids and gases, molecules can also move around from region to region like a river or a cloud. The movement of objects is quite a cool notion. It's kinetic energy. Come on! Molecules in motion.
Molecules are moving all the time.
Molecules in motion.
Molecules, they keep us energized.
Okay, kinetic theory and gas laws. Wasn't that a great video? Okay, Roman numeral number 1 on your notes, kinetic molecular theory, KMT, just abbreviate it. It says that the particles, the atoms, and molecules are in constant, random motion, and the motion of the particles determines what phase it's in, solid, liquid, or gas. Okay, you guys have done this before. If your hands are atoms or molecules, if it's a solid, they're stuck together. There are strong intermolecular forces that hold the molecules and the atoms together, and they vibrate back and forth. If you heat them up, they vibrate faster. If you heat them up, again, why does it tell me this all the time? I was in the groove, and it's messing me up. Okay, molecules. If they're in a solid, they vibrate. You heat the solid, and they vibrate faster and faster. If you heat it up more and more and more, they'll vibrate so fast that they break apart. And now you've changed it from a solid to a liquid. So the liquid molecules have a great more range of motion than the solid. So they're constantly touching. There are still some strong intermolecular forces that kind of hold them together. Bonds, or not bonds, but forces between molecules that attract molecules together. So if we heat up the liquid, it goes faster and faster and faster and faster and faster until it breaks apart. That was a sound effect, by the way. It breaks apart, and now you have these molecules going every which way, and that's what the gas is. So determining how fast the molecules are moving will also help you figure out, is it a solid, a liquid, or a gas. Now, how do we increase the motion of the molecules? We add heat. Alright, so kinetic energy is the energy that's due to motion. And there's an equation with it. You guys learned this in IPC. If you've already taken physics, you've already had this equation too. So kinetic energy is 1/2 times the mass times the velocity squared. So the units are kind of strange. The units are called joules. And what it actually is kilogram for mass. And velocity is meters per second. But if you square it, you get meters squared over seconds squared. So it's a strange looking unit, and somebody got tired of writing that out multiple times, and so they said, hey, let's just call it a joule. We named it after someone. Alright, so Roman numeral number 2 on your notes, gases in the kinetic theory. There are some properties of gases that you need to know about, and some of these properties you guys already know already, and some of them are new. So capital letter A on your notes, the properties of gases. Gas particles are far apart compared to how big they are. So there are spaces between the gas molecules. Now remember, these are tiny, 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 tiny. But so small that it's difficult for us to kind of get a picture in our heads. Collisions, you get two things, you smack them together and you have a collision. Collisions between the gas particles and the container cause pressure. And now it also says they are elastic, which means that there is no energy lost when the gas particles hit the containers. So what causes pressure or gas pressure or air pressure? It's when the gas particles hit the container. If we talk about, well, gosh, in the classroom there's no container. Well, in essence, the Earth is the container, and you are part of the container. So gas molecules or particles hitting you create air pressure on your skin, too. You were born into this air pressure. You know what it feels like. You don't know what it feels like without that pressure. Number 3, gas particles are in continuous motion. They have lots and lots and lots of kinetic energy. They have the ability to flow, so they're considered fluids. Liquids, remember, liquids also have this ability. So when we talk about fluids, we talk about gases and liquids. And I have another video. I really hope this stuff works. Otherwise, I'm going to be really irritated if I have to do all this over again. Oh, what happened? Let's go back one. Let's see. There we go.
Take a sip. Change the shape of it. Step on a fluid and through it you will slip. If you're a liquid or a gas, you're a fluid. If your ship will not last, you're a fluid. If you're the air we breathe, then you're a fluid. Now fluids can change shape, flow around and circulate. Take a liquid or a gas and you will know what you have. A fluid. Fluid's good. If the container is around, so's the fluid. The air moves all around, cause it's a fluid. The water's pouring down, cause it's a fluid. We need fluids. Fluid's good. I like fluids. Fluid's good.
Okay, that would be Bill Nye from the Bill Nye Science Guy videos. And I know you guys are too young to remember because you weren't even around or a thought. But that's a parody on the group Devo. Alright, letter B, they exhibit diffusion. So gases show diffusion. Now, so do liquids and solids, just not very fast at all compared to the gases. So liquids are much faster than solids, and solids, when they diffuse, you're talking years for them to diffuse. And diffusion, number 1 there, diffusion is the random movement of particles from an area of greater concentration to an area of lesser concentration where they spread out. Now, there's a special type of diffusion that you guys should remember from your biology classes, and typically you can't shove it out of your brain. You need to keep up with this word because it's going to be in pretty much any science class you pick up. You're going to hear about this word osmosis. And osmosis is the diffusion of water through a semi-permeable membrane. In biology, you talked about it being through a cell membrane. So diffusion is kind of a generic word, movement of molecules or atoms from an area of greater concentration to an area of lesser concentration. And osmosis is just a type of diffusion. Alright, there are no forces of attraction between particles, gas particles. So that means there are no IMFs. IMF means intermolecular force. So it's kind of like you have maybe all these water molecules, and they're attracted to each other. And because they're attracted to each other with simple little hydrogen bonding, we'll talk about that too, they kind of stick together a little bit. That's why you can take a paper clip and set it on top of the water, and it's not floating, it's actually not breaking the surface tension. Or you see those bugs that are walking across the water. There are IMFs, intermolecular forces. They're nothing like the ionic bonds and covalent bonds and metallic bonds, but they're strong enough that we can see an effect. Gases don't have those at all, nothing. So because there are no forces of attraction between gas molecules, they expand easily and they completely fill their containers, and then it's easy to compress them too. So compared to solids and liquids, gases don't have those intermolecular forces. Solids and liquids have a lot of intermolecular forces, so they don't move around as freely as the gases do. Gases have a density of about 1,000 times less than their solid or liquid phase. So if you take a particular gas, let's say iodine in a gas form, and compare it to iodine in a liquid form, it's going to be 1,000 times less dense. Remember, density is how much mass is packed into the volume. So gases just spread out. They can take up a lot more volume. And number 6, the average kinetic energy of gas particles depends on the temperature of the gas. And again, if you look right here, we have that equation. Kinetic energy is equal to 1/2 times the mass times the velocity squared. Okay? And since if we talk about one particular gas, we don't change the mass of the particles. Really, then we talk about how fast the particles are going. So it's really the speed, the velocity of the particles that is measured, basically, in a roundabout way when we talk about temperature. Okay, so using the kinetic molecular theory, explain why a tire blowout is more likely to happen on a trip in the summer than on one taken in the winter. You can pause this and answer this question in your notes. And the second question, use the KMT to explain why on a cold autumn morning a camper's air mattress may appear to be somewhat flatter than it was when blown up the afternoon before. And, there are no leaks in the camper and the air mattress. So basically what it's saying is the evening before when it was warm, you blew that air mattress up, and then the next morning when it's cold, it seemed to be kind of flat. So pause this and try and answer that question. Okay. Now, there are some kinetic energy calculations here. Kinetic energy is completely dependent on the speed of the particle because the mass of the particle, when we're talking about one particular gas, it doesn't change. So KE is 1/2 m. Mass is going to change. It's the velocity that's going to be dependent upon it. So an increase in temperature means an increase in the speed of the molecules and vice versa. You increase the speed of the molecules, you increase the temperature. All gases, and this is really cool, all gases at the same temperature have the same average kinetic energy. Well, what that means is if you have gases like a mixture, then the lighter gas particles are going to have to be zipping through there really fast. And the heavier gas particles aren't going to be moving as fast. If you look at them all together and they have the same average kinetic energy, so that kinetic energy isn't changing, the mass of the individual particles, they're not changing, so it depends on the speed. And the big ones are going to move slower than the lighter ones, and that just makes sense. Okay, we talk about an ideal gas and a real gas. Ideal means like it's perfection. And an ideal gas, you guys all know, there's no such thing as perfect in there. So we talk about our equations, and we usually talk about an ideal gas, and it's an imaginary gas that fits all our perfect little rules of the kinetic molecular theory. Real gases don't behave completely according to the rules of the kinetic molecular theory, but you can usually only notice that at really extreme pressures and really low temperatures. So for the most part, room temperature or standard temperature and pressure, it's going to be just fine. We can use the ideal gas law and it's going to work for everything.